History is measured in thrust. Before humanity could walk on the moon, we had to build the stairs to reach it. This is the complete lineage of NASA's lunar launch vehicles, a 60-year evolution from desperate experiments to the most powerful machines ever engineered. The journey began in the late 1950s with modified missiles. The Thor-Able and Juno 2 were the pioneers. The Juno 2 was a study in crude ingenuity. It utilized a spinning tub cluster of solid fuel upper stages. It had to spin like a top just to maintain stability as it clawed its way out of the gravity well. Then came the Atlas family. These machines were engineering marvels known as balloon tanks. Their stainless steel skins were thinner than a dime, kept rigid only by internal pressure. If the nitrogen pressure failed, the entire rocket would collapse under its own weight. But the true revolution was the Atlas-Centaur. It introduced liquid hydrogen, a volatile, high-energy fuel. To keep it from boiling off, the rocket was wrapped in insulation panels that jettisoned during flight, a complex shedding of skin that unlocked the energy density required for deep space. Before astronauts could land, robots had to scout. The Atlas Agena and Atlas Centaur became the workhorses for the Ranger and Surveyor missions. They proved that the lunar surface was solid ground, not a quicksand of cosmic dust. While robots mapped the path, engineers prepared the riders. Little Joe 2 was a squat, solid-fuel brick designed solely to test the Apollo escape system. In contrast, the Titan II GLV was a refined weapon of war. It burned hypergolic propellants, chemicals that ignited instantly on contact. No sparks, no ignition systems, just pure, reliable violence. It carried the Gemini crews, teaching NASA the orbital ballet of rendezvous and docking. But to take heavy hardware to the moon, we needed monsters. The Saturn I proved the concept of clustering engines, bundling 8 H-1 motors and tanks into a single stage. Its successor, the Saturn I-B, became the Apollo workhorse for Earth orbit. To launch from the massive pads built for larger rockets, the shorter Saturn I-B often stood on a steel pedestal nicknamed the Milk Stool, bridging the gap to the swing arms. All roads led to the Saturn V, the apex predator of rocketry, 363 feet of vertical ambition. Rolling out on the crawler, it weighed 6 million pounds. At its base sat 5 F1 engines, the most powerful single-chamber liquid-fueled engines ever flown. When these ignited, they didn't just fly. They altered the atmospheric pressure of Florida. The engineering behind the stage separation was critical. Retro rockets had to fire precisely to push the spent heavy metal away from the delicate spacecraft, a choreography performed at hypersonic speeds. After Apollo, the giants slept. But the mission continued. The Atlas V and Minotaur V returned us to the moon robotically, launching the Lunar Reconnaissance Orbiter and LADEE missions to hunt for water in the eternal shadows of the poles. Now, the silence breaks. The Space Launch System, or SLS. It resurrects the shuttle's RS-25 engines and solid rocket boosters, stacking them for pure power. The Block 1 generates 8.8 million pounds of thrust, surpassing even the Saturn V. The future Block 1B will introduce the Exploration Upper Stage, a massive second stage designed to push heavier habitats to the Lunar Gateway. And on the horizon, the paradigm shift. SpaceX's Starship HLS, a stainless steel tower designed to refuel in orbit and land vertically. From the fragile balloon tanks of the 1960s to the reusable steel of the Artemis era, this is not just a timeline of rockets. It is the evolution of our species' will to ascend. We build these giants not to conquer the sky, but to secure our future among the stars.